All right, fellas. Okay, I'd like to bring your attention here. Okay, so this is the example that we'd like to try on. Okay, this example will explain to you how we shall use the momentum equation. Okay, how we shall use the linear momentum equation that we just learned. Okay, in theory. All right. Um, okay, reducing elbow. Okay, the force to hold deflector elbow in place. Now, okay, why do you think that we need to study about the force, about the momentum? Okay, about the momentum, fellas. Okay, we're studying about momentum, right? We're studying about the force. Why is that? It's actually one of the application is actually to hold, to know how much force do we need to design something in order to hold this elbow. You know what's the function of this elbow? You have water running through it and then being accelerated a little bit and then pointing upwards. Okay, this elbow is sometimes used to deflect. Okay, to deflect water. Okay, at a certain angle. Perhaps the sprinkler and then is pretty much using the same principle here. So you have water running possibly in a bigger tube, and then it's rushing outwards. Okay, rushing outwards in angle. Okay, in angle. So this is one of the best example, okay, of a deflector. So you have water running inside and then water running. Okay, now we can read the the whole situation. Okay, we can read the whole situation here. Okay, the force to hold a deflector elbow in place. Okay, this is the schematic diagram of a deflector elbow. Just so you know that the function of the deflector elbow is to deflect the water, okay, at certain angle, okay, depending on the application. All right. Okay, we call this a reducing elbow because the diameter is reduced, okay, towards the end. Okay, you have big one and then you have smaller ones. A reducing elbow is used to deflect water at a rate of 14 kilogram, okay, per second. This is the mass flow rate. Okay, in a horizontal pipe upward 30 degree. Okay, this is the degree, 30 degree, while accelerating it. Okay, while accelerating it. Okay, a reducing elbow is used to deflect water flow at a rate of 14 kilogram per second in a horizontal pipe upward at 30 degree. Okay, this is a straight 30 degree while accelerating it, like I told you. Okay, because they reduce the exit. Okay, is increasing the velocity. The elbow discharges water into the atmosphere. Okay, it gives something here for you to ponder. Atmosphere. The moment we use the word atmosphere, meaning point number 2 here, the pressure at point number 2 is equivalent to the pressure at atmosphere. Okay, that's basically what it means. The cross-sectional area of the elbow is at the inlet is 113 centimeters square. Okay, at the inlet, and then you have a 7 centimeter square at the outlet. Okay, so it's wow, it reduced quite significantly. This is 113. This is only 7. The elevation difference between the center and the outlet, okay, and the inlet is 30 cm. Okay, so the inlet, okay, the center, and then this center, okay, this center of the is 30 centimeter, and this center is okay 30 centimeter different. The weight of the elbow itself, and the water is okay, considered to be negligible. Okay, we just concentrate on the water here. Determine the gauge pressure at the center of the inlet at the elbow. Okay, the gauge pressure. Okay, we need to determine the gauge pressure here. Okay, at P1. Okay, the center of the inlet of the elbow. Okay, so we're gonna put this elbow here, and then the anchoring force needed to hold the elbow in place. Right. Say that we need to determine the gauge pressure at point number 1. We know the point number 2, it equals to PATM, right? It's no question. We need to know the pressure at point number 1, all right? Because it's not given. And then the anchoring force needed to hold the elbow in place. That is the force needed to support the momentum of the liquid. Okay, that's basically what it means. Okay, the force needed to support the momentum due to the movement of the fluid. Okay, MV1, right? Okay, in this case. So that's basically what we are trying to find out. Okay, that's basically what we're trying to find out. Now, okay, well, actually, this example is quite, I would say, is quite straightforward. In order to find the P, fellas, I think you learned this in chapter 5, yeah, with Miss Ain, if I'm not mistaken. You have to use the moment you have two states. Okay, state one. Okay, point number one along a fluid flow. You have point number one, and then you have point number two. Okay, of fluid flow. You can directly use Bernoulli equation, fellas. Okay, I repeat. The moment you have this, okay, you have a water flowing along the channel or whatsoever. Okay, and then you have the characteristic at point number one. You have the characteristic at point number two. You can use Bernoulli equation directly in order to find all the information related to it. In fact, you know what? The Bernoulli equation. Okay, this is the Bernoulli equation, right? The Bernoulli equation. Okay, Bernoulli equation. This is the Bernoulli equation. Okay, the Bernoulli equation, right? Okay, let's make it bigger. The Bernoulli equation: P over rho G plus V square over 2G plus Z. Okay, if I'm not mistaken, all right? Okay, over 2G plus Z. Okay, this is point number one. And then you'll have something similar at point number two. All right, this one is equivalent to P over rho G plus V square over 2G plus Z2, right? For point number two. Okay, you can, this is what we call the Bernoulli equation. Okay, Bernoulli equation. This is called the Bernoulli equation. Okay, Bernoulli equation. The moment you have water flow, and then you have water flow, yeah, this is water flowing. Okay, if you need to find all the information at point number one, at point number two, this is the equation that you can use, right? If P is you need to find, you can use this equation. If V is you need to find, you can use this equation. If the whatever, I think G is given. Okay, don't have to worry about. If the elevation is that the one you need to determine, this is the equation to use, fellas. Okay, if you need to find anything related to any of the parameters in here, then you can use this equation, right? In this case, especially, you have water flow, point one and point two, then you can determine the parameters that you need to determine. And furthermore, in this case, it says that you need to find P1 equals to question mark, right? Point one, P1 equals to question mark. Thus, how do you find P1 values? How do you find P1? You know that P2 exposed to the atmosphere, right? Okay, have a look at the figure. Have a look at the figure. Okay, P2 is directly exposed to the atmosphere. Thus, P2 equals to P ATM. Okay, P2 equals to P ATM. P1 is what you're trying to find. And then the Z, I think the V1, V2, is it given? Okay, let's go back to the V1. V1, V2 is not given. It's only giving you the cross-sectional area. That's even better, because the moment you know the flow rate, m equals to rho AV, or Q, the V dot equals to AV. Okay, you can find the velocity. See, m equals to rho AV. Okay, m equals to rho AV1, m equals to rho AV2, just to fulfill whatever that is missing in here. Okay, you can find, I think you can find here, you can find the elevation. Okay, the elevation in terms of is 30. Okay, the Z1, of course, there's no elevation. Z2, yes, elevation 0.3 is given. Okay, it says that the elevation is from the center towards this center is 30 centimeter, is 0.3 in meter. So 0.3 minus this is the speed. You have to calculate the speed. V1, m. Okay, where this V1 coming from is actually m equals to, okay, m equals to rho A V. Okay, if you need to find B, V equals to rho A divided by m, the mass flow rate. Okay, what will be the mass flow rate in this case? Is the mass flow rate given? Okay, 14 kilogram. Okay, let me ask you a question. What will be the mass flow rate at point number two? okay, it's the same. When you have one inlet and one outlet, okay, assuming that this one is steady, then you will have okay, elbow. You have this one same. The mass flow rate at point number one, point number two is the same. So that is why you see this one here is 14, this one here is also 14. Okay, point number two. So it's the same water. It's just that is the area that is different. Okay, it's the area that is different. So that's why the V1 you get 1.24, V2 you have 20.0 meter cube, right? And then you find the answer, you put in all values using the Bernoulli equation. The Bernoulli equation, like I told you, is applicable the moment you have a fluid flow. The moment you have fluid flow, point one and point two, you can use this equation right away. Okay, you can use this equation right away. And then you just find anything missing. I think this one is straightforward. We're not going to discuss this because I believe that you studied this with Miss Ayn. Okay, this is what you have already learned. Okay, I really hope so. Okay, that you understand. Okay, the use of Bernoulli equation, right? Point one, point two. Okay, so you have all the corresponding parameters. So you just find the one that's missing. In this case, it's obvious that it's asking to find P1, which is in this equation, right? P1 is here. P at point number one. So P at point number two. So you just calculate and then you get P. I think it's quite straightforward. We're not going to go here, right? We're not going to go here. I think if I were to ask you, just find the P. I think that is the easiest one of all, right? Okay, that is understandable. Okay, P1. Okay, we get it directly, but my attention is at point B here, the momentum equation. Okay, for the flow. Where do you think this is coming from, fellas? Where do you think this is coming from? This is by assuming that the flow is steady. Okay, let's have a look at the lecture notes. Okay, this is where we refer to the equation, right? Okay, like I told you, this is the equation, right? Okay, this is the equation. Okay, the real equation, the full equation. Okay, you have the force acting on the control volume, and then you force acting on the surface, right? Okay, so you have if you were to expand this, no, I think it's here. Right, okay. The correction factor with correction factor. If you were to expand this, okay, this is what you get. Okay, F equals to this for the body, and then this is for the surface. Yeah, body and surface. Where they get the body and surface, I think is from the initial equation, I believe. Okay, yeah. This is the body, this is the surface. Total force acting on the control volume equals to the force of the body, force of the surface. This is the force on the control volume, this is the force on the surface, all right? And if you put it down in equation, so this is how it's going to be. Force, okay, the control volume, this is the body, this is the surface. However, for control volume, this bit here,
Sir,
oh, yeah.
the screen is not.
Okay, I'm not sharing the screen. Sorry. Yeah. Okay. Where was I? Right. Let's go back to the lecture notes. Okay, lecture notes tells you that this one here, right? You have force acting on the control volume. You have body, and then you have the surface. Force acting on the body, that is force acting on the control volume, and then force acting on the surface, right? I think is easier for you to say it now, right? Okay, and then to expand this, right? This is how you expand it. Okay, this is how you expand the equation. Okay, this thing, yeah, this is how you expand the equation, right? You expand this equation, now this is what you're going to get with the correction factor. Okay, this equation, like I told you, this is the equation that you shall use. This is for the control volume, okay, of the body. Okay, when you have gravity, I told you this is mostly gravity, okay, for the body itself. And this is on the surface. Again, it depends on the outlet flow, okay, minus inlet flow, right? Okay, outlet flow minus inlet flow. That is the mass flow rate of the outlet multiplied with the volume, with the velocity. Okay, mv is the product of momentum multiplied with the correction factor. Okay, correction factor. This depends on the type of velocity profile. If it's turbulent, it's one. If it's laminar, and it's definitely not one. Okay, so you minus this. So this is the equation to use. And the equation is even simpler for steady flow devices. Why is it simpler for steady flow devices? Because of this, because of Newton's third law. Newton's third law saying that, okay, Newton's third law, when the body exerts a force on the second body, okay, the second body exerts equal or opposite force, okay, on the first. Meaning, if you have momentum going this way, you'll have another momentum that is opposite. Okay, that is opposite it, right? Meaning, the body itself, the momentum of the body due to the flow itself becomes zero. So that is why in this equation, this one here, that one acting on the body, the momentum becomes zero for a steady flow device. Okay, so that's why for a steady flow device, this is the equation to use, right? Why? Because the body is the force on the body is negligible, and this is the equation that you can find this, okay, in this exercise. Why do you think that this equation is used? Why? Because we are assuming that the flow is steady. Okay, that's why you have this bit here. All right, that's why you have this bit. Now, okay, now you need to expand this. No, you see this, the direction. You still are you seeing this? The direction here. All right, this arrow. Okay, this arrow on the head of the F. Okay, is actually referring to direction. Direction of the force. Direction of the velocity. Direction of the velocity of the outlet. Direction of the velocity of the inlet. Now you need to expand this equation. Okay, you need to expand this equation. Now have a look at here, right? Have a look here. You know that the flow is going in this direction, is going straight in the beginning and then upwards, right? We are analyzing this. Okay, this is the hard bit, right? The flow at first, okay, in inlet, it flows steadily, okay, in the x direction. Okay, just in the x direction. Nothing in the z direction. No, just in the x direction. And then as it moves out, okay, we just viewing on the at point 1 and point 2. Forget about the one in the middle, right? We just view the one point number 1 and point number 2. Point 1, you just have force in the x direction. Okay, you just have force in the x direction. At point 2, you have force or you have momentum in both direction. You have direction in x direction. You have direction in z direction, fellas. Okay, let us try to analyze this. If you were to ask me, first is the force, right? Let us study about the force. You have force in the x direction at point 1, but you have nothing on the going upwards, because we know that force is going this way. Okay, however, as it moves at point number 2, force is heading in this direction, right? Okay, in this direction. Force, this is the normal force. And then for this, I think you need to develop the component in the x direction as well as z direction. It says z here, not y. Okay, it says z. So you need to expand the f, okay, in the x direction at point 1. Okay, at point 1. All right. Okay, and as well as point 2. All right. Okay, so we need to expand the force. Okay, like I told you, this the f here, okay, with direction, we need to expand them in the x as well as in the z direction first. You need to rewrite this equation in x as well as x as well as z. Okay, that's basically what we are doing in this, okay, example. F, okay, the sum of all the forces acting on it. Okay, the sum of all the forces acting on it, right? Okay, the sum of all forces. Okay, force number 1 is obviously fx. Okay, fx going in this direction. That's the first force. Okay, and then plus another force. Okay, plus another force. Okay, plus another. Okay, this is in the x direction. Plus another force. Okay, with regards to the pressure. I think we just calculated that there's pressure on this right. Okay, this pressure on this side. There is actually P1 plus ATM in this instance. Is P1 plus ATM. P2 you have pressure as well. It's just P2 equals to PATM, right? This one is P plus PATM. This one is just PATM. However, I think we decided earlier that we're gonna cut the where is it? We're not gonna use. Yeah, okay. We're not gonna use the atmospheric pressure, because it's pointless. It cancels out in all direction. So that is why we're just gonna evaluate the force. Okay, the force, the gauge, a force that is brought by the gauge pressure. Okay, force that is brought by the gauge pressure. Okay, so that's why you have this. Okay, just in the case you don't understand this is actually force exerted by the gauge. Okay, in this area. Okay, you have force here, right? Okay, this is the force exerted by the gauge. Okay, by this area, point number one here. Okay, you have P1 minus P ATM. This is P ATM. However, you cancel out the P ATM, remaining is P1. P1 is actually exerting some force on this area at point number one. So you have to consider this force. So that is why you have P1 multiplied with the area. Okay, you have the force. Because why P1 multiplied with the area? Why P1 multiplied with the area? Why do you have, okay, first is the sum of all the force, okay, of the force in the direction equals to, okay, equals to, what's the formula? Okay, this out minus in, the sigma of mv, okay, minus mv, okay, out. This is inlet, this is outlet. And then you have beta, okay? So the sum of all the, this one is the same, yeah, beta mv in, beta mv out. So this is the equation, I believe, okay? If I'm not mistaken, yes, mv, yeah, the mass flow rate, okay? M in the direction, okay? So there you go. Right, so F, you need to expand this in the F direction. You have Fx, okay? This is the force that we are trying to find, okay? The force that we're trying to find in the X direction, fellas, okay? In the X direction, this is the F in the X direction. Okay, just say F in X, okay, they use R, doesn't really matter, just Fx, okay? Plus the force that is acting here, right? This is the only force that's acting at point one, because like I told you, we are just looking at point one, point two. Point two, no force, because a P ATM. So there's only one point here, okay, acting on it. So Fx, okay. Y, okay. Pressure equals to F divided by area, right? Okay, pressure is actually P equals to F, the force, divided by area. So that's why force, if we are sum of all the force acting in the positive x direction, we are assuming that this is positive, right? Going that way is positive. So Fx, okay, assuming that that way is positive. So F equals to P multiplied with area. So that's why you have the second phase here. It's obviously P exerted at point number one multiplied with its area. So it's actually force here. Okay, it is actually force. Okay, it is actually force. Okay, in the x direction, acting at that point as well. Okay, so these are all the forces. Okay, the sum of all force in the x direction. This is x direction. Okay, x direction. Okay, this is x direction. Oops. Okay, I have to write everything in. Okay, force in the x direction. Okay, equals to and this mv in, mv out. Okay, you have the mass flow rate in, which is given directly. We have the mass flow rate. What about this? What about this value? This value, how much is it? How much is it? Okay, how much is it? How much is it? I think this one here, you have, it depends on, like I told you, the velocity profile, right? Whether it's turbulent or whether it's laminar. In this case, the book is assuming, okay, the book is assuming the flow is turbulent. Okay, flow is turbulent at the inlet and the outlet of the volume. And then they take the correction factor to be 1.03. Okay, the correction factor is taken as 1.03. Right? It's taken as 1.03. So that is why, okay, you rewrite this equation. Okay, you rewrite this equation. Okay, you rewrite this equation. Okay, you expand them. Okay, you expand them in the x direction. Yeah, okay, in the x direction. Like I told you, you have to write everything in the x direction. So you have, no, this one is out. Sorry, this one is out. So it should have been out, yeah? Out minus in. This one is out. Let's go back to the equation. Yeah, this one is out. This one is out. This one is in. Okay, this one is out, this one is in. So if you were to put them, okay, this one is in the x direction. Okay, this one is in the x direction. Okay, you have expanded all the F, okay, force, okay, acting on the x direction. And then how about the left-hand side? The left-hand side here, you have to write this one down. So the sigma won't change, the M won't change, okay? How about the velocity at the exit? Velocity at the exit. Now, if you go back here, like I told you, is going in this direction, right? It has the x component, it has the y component. Okay, as for the x component, it is v cos theta. Okay, is v cos theta, right? Is the v cos theta. Okay, is the v cos theta. So that is why v here is the v cos theta. Okay, is the v cos theta minus, okay, the beta m, okay, multiply with, okay, so okay, let's go back to the inlet. Let's go back to the inlet. What's the inlet like? Okay, inlet, you have V here. Do we have to write like V cos theta, V sin theta? No, there's no angle. V is strictly in this direction, is going in this direction, just in X direction. Okay, just in X direction. So that's why you have the V here. V is just V. V, in fact, this one is V1. Okay, so this is the equation. This is the equation for you to solve. And then the moment you solve this, you will find the force in the x direction needed, okay, to support the momentum, okay, coming from the fluid, okay, at this point number one. Okay, at this point number one, right? So that is your answer. If you find the answer, you find P1, which is we have calculated earlier using this Bernoulli equation. The area, I think area is quite straightforward. B, the book is using 1.03. The mass flow rate, I think it's the same for inlet and outlet. Just that this one here, okay, is what they call that, is angled. The velocity is angled. Okay, again, yeah, okay, again, velocity, I forgot. Okay, something I forgot. The velocity. You need to decide on the direction of the velocity. Okay, I forgot. Okay, V is with the arrow at the top, right? Arrow at the top. So V is, okay, we are assuming that V is going in a positive X direction. So thus, you know what? Actually, the right one to put is, the right equation to put is actually rho M positive V. Okay, positive V cos theta. Cos theta minus rho m positive v. Okay, positive v1. Why positive v? Because it is it is in x direction. Okay, it is in x direction because in you'll see in different exercises they practice this. Okay, they practice this. Okay, they practice this. Okay, why positive v? Because it's flowing in positive x. You have, okay, you have the axis. This one is a z, sorry, not y, z and x. This, if like going this direction is positive, if it's going this direction is negative x. Okay, as for the z, going upwards is positive, going downwards is negative. Okay, so that's why you have this. So if this is the equation in the x direction, have to finish? No. Okay, we have not considered other Cartesian coordinates. Okay, we have to expand the f. This is the equation. We need to expand the one in the z direction as well. We have the x and the z, right? Okay, then we expand the z. Okay, we expand the z. Okay, with respect to the f. Okay, the f for the z, f in the z direction is equivalent to, all right, the sum. Okay, the sum is, okay, f in the z direction equals to the sum of, okay, something similar. Okay, something similar. Okay, this one is the rho m so no rho, beta V, okay, out, okay, minus MV in, right? Same thing, sounds better. Okay, same thing, right? Same thing. This is what you do. Okay, for the Z direction, okay, for the Z direction, okay, then for this one you have outlet, yes, you have the beta M V positive V sine theta. For the inlet, what's the inlet, fellas? What's the inlet? At point 2, yes, you have the V sine theta, okay? There's no pressure at point number 2, right? How about this one? Do you have anything at point number 1 here? Do we have anything in the Z direction? Do you have anything in Z direction? No, because the water is strictly flowing in this direction. So that is why you only have this minus 0, minus 0. So that is why FZ, okay, Z, according to the book, you only have M V sine theta. Okay, V sine theta. Okay, V sine theta. Let us check. Okay, so the FV just V V2 sine theta. Okay, V2 sine theta, right? Okay, we're talking about point 2 there. Okay, V2 sine theta. Okay, I forgot that, right? V2 sine theta. Because at point inlet, this is 2, this is 1. This is nothing, it's 0. This one is 0. So that is why it's V2 sine theta. Okay, so that is your answer. You try to solve, you get fx. You try to solve, you get fx. Okay, and then you get fy. Why do you think you don't have this? Okay, in fz, because at the inlet is 0. Okay, it's nothing there, right? This is only at inlet, right? Because we neglect all the p at the m. So this is the only bit that you have for the z direction. So if you go back to the equation, okay, this is the in the x direction, the force that is required to support the momentum is given by this in the x direction, and this is in the z direction. Now, next is for you to solve this. You put in all the values, okay? I believe you have all the values, right? You have the V1, you have V2, you have cos theta, of course, is given directly. The beta, the mass flow rate is the same for inlet and outlet. You just put them in, and then you will get your answer, okay? Negative here, it says that, okay, our initial, we say that the force is acting on this direction. In fact, it's acting, okay, initially we assume, okay, we assume that x and z, okay, we assume that the force is acting this way. However, based on the calculation, the force is acting on the other side. Okay, the force is acting on the other side. That's what it meant by negative. Okay, you don't have to worry about the negative. Okay, and then after calculation, FZ is 144, yes. Okay, meaning 144 is correct. We initially assumed that in Z direction is acting this way. Yes, it is correct. FZ is acting this way, and then FX is acting in this direction. So that is basically what it meant by this calculation, fellas. Okay, I'm done for the calculation. Now, question and answer, right? So what do you think of this? Simple? What do you think of this, fellas? I'm just gonna stop here, right? I'll stop just here, right? If I could continue, you'll have depression. Okay, if I continue, I know that you're gonna have depression, right? I know it's tough. I know it's hard, right? If you're not listening from the very beginning, if you don't even know what Bernoulli equation is, I feel for you. Okay, I feel for you, to be honest, right? If you don't know what Bernoulli equation is, right? This is, I think you know the reason why I'm putting this chapter towards the end, right? Okay, I know, right? Okay, to make you even happier. Okay, okay, what do you think of this, fellas? Hard? Senang? Kalau senang, you memang hebat lah. Okay, kalau senang, you
Very
memang hebat.
hard.
How do you think of this? Hard? Manageable?
Manageable.
Manageable, yeah. I think I really hope this is manageable for you people, right? We're just gonna stop here. If I drag on, we have lots more exercise. In fact, and are you ready for your quiz, fellas? You guys ready? If I were to give you the example, the similar example, would you be able to do it? Would you be able to do it?
Yes.
All right. Okay,
Yeah.
I can see some confidence there. All right, but not similar though. I'm not saying it's similar, but the analysis could be similar. Okay, the situation could be plenty. It can be many situations that you're dealing with. But then again, in terms of how you perceive the situation, how you analyze the situation, whether they will be like whether it's going to be steady. Okay, if steady, what happened to the equation, the whole equation, all right? Okay, so there are many things, okay, that you have to understand, right? That you have to understand, okay, and how you're doing it, right? Okay, technically, if you ask me, I think it's quite challenging though, right? It's quite challenging. Okay, it's not easy. It's not that simple either, right? It's not simple either. For me, okay lah, okay. I'm not saying this is hard, but then again, it's manageable, like you just said. Some confident ones just said it's manageable, right? I think if that is the case, okay, if that is the case, allow me to share this with you. Mm, okay, allow me to share this with you. Okay, momentum analysis question. Okay, I have the book example. Okay, I am going to enable it now, right? The book example that we just did, all right, you can find in the book example. Okay, you can have a look at the exercises, but then I'd like you to do this one as well. Okay, I'd like you to do this one as well. This, okay, I take this as your homework, right? Please refer to your ellip, fellas. Please refer to your ellip. I want you to, okay, the exercise that we just did together, you can find in the book example. Is actually an example from the book. And then I want you to do the 6.1 here, right? I want you to do this 6.1. I'm going to give you the example. In fact, we're going to try, we're going to discuss about the example. It's quite similar to what we just did. However, um, um, it's with a little bit of trickery. Okay, this question is with a little bit of trickery. It's simple. It's straightforward in terms of the analysis. It's pretty much similar to what you just did, but okay, I know that most of you will not be able to get this one right. Okay, I think we you try doing this one. Okay, submit your answer. I just want to see it. Okay, I just want to see it. Okay, and then we shall try. Okay, we shall try on it. All right, together in our next class. Okay, in our next class. Okay, try doing this now. You still have like a few minutes left. Okay, a few minutes left. Okay, I'm just gonna stop here. I'm not gonna drag any longer because if I drag any longer, you'll be in depression. Okay, this chapter is quite challenging. Okay, like I told you, if I finish any chapter, I'll put in what do you call that, self-reflection. Okay, I just need to know what have you understood. Okay, I just need to know what have you understood out of the previous chapters that we did. In fact, I'm going to put all of this, okay, the reflection of the dimensional analysis modeling, reflection on the internal flow, as well as reflection on this. Okay, so try look back at what we have studied in internal flow, and then try to write in what have you understood, okay, out of the internal flow. And as for the momentum, I know it's challenging, right? But I suppose that it's still doable, it's manageable, all right? It's not that difficult, right? Don't think this one will be a burden for you, okay? Because the moment you think it is, then it's going to be challenging. Okay, so I think those who have not scanned your attendance, please do so. And then if you need my no attendance, please let me know. Okay, so I believe that will be it for the lecture. Have you got any question for me? Ada soalan before we end the session? Well, actually, from the look of it, I think we can finish in our next class. Okay, we can finish in our next class. Okay, we can finish this chapter in our next class so that you can have your preparation. You can have your preparation. I'll be uploading your assignment next week, right, on Monday. Okay, on Monday during the class, I'll be uploading the assignment. Okay, that is when I'd like you to do the assignment as part of your preparation for the test. Okay, as well as the final exam. Okay, so that will be it, fellas. Okay, that will be it. Okay, thank you very much. Ada soalan tak ada. Let me check. All right. Okay. So if we don't have any question for me, I believe that will be all for the lecture. Thank you for joining me this afternoon. All right. Thank you for joining me this afternoon. And then I wish you all the best. All right. For your test, for your assessment. I know you have many tests, many quizzes, many assessment, many assignment. So please don't miss the class, fellas. Okay. I've seen quite a lot of you missing your class. Okay, that could have like a severe impact on your understanding, okay, for the course, right? Please attend the class as much as possible, because the thing that we learn in the class, sometimes I give you tips. I'm teaching you how to understand, right? I'm not. I'm teaching you how to understand the equation rather than rather than memorizing the equation, right? Because I want to become an engineer later on, you don't have to memorize the equation. Okay, the equation is there. It's just a matter of how you understand how to use the equation, okay, for proper use. So that will be it. Thank you very much. I'll be seeing you again, inshallah, on Friday. Okay, 8:30 as usual. Then till then, take care. I'll be seeing you again, inshallah. Bye bye.